I'll be presenting this work that was published at Infocom in QNAP's workshop this year that surrounds research that I've been doing over the past year on quantum error mitigation, particularly in the context of global and local encodings. So just to set the scene, the setting in which I work with and the setting which this paper is focusing on is distributed quantum computing. In this setting, we assume that we have a very large computation that doesn't fit into individual quantum computers and therefore needs to be partitioned or cut up in order to fit individual devices. These devices will therefore have as an objective completing this computation in a coordinated fashion. In order to do this, there is a pipeline that needs to be followed. So we start with a large computation, we abstract it to a setting in which it can be partitioned. This is usually a hypergraph. This hypergraph is cut up, and then the sub-circuits that arise from the partitions are assigned to different devices within a network that interconnects them. Now, quantum computation is limited by noise. This is arguably the biggest problem that the entire field of quantum technologies is facing, and it's this reality that qubits are very delicate. In a distributed setting, we not only have to deal with device noise, but we also have to deal with network noise. So every single time we need to do an operation that requires coordination or a collaboration between two devices, which is very often, we are going to introduce additional noise on top of the one that already exists within our devices. This is a massive issue that is really been underexplored in the DQ setting. Noise management is fundamental to the viability of the proposal, yet the question remains really unexplored. There's a few reasons for that. The first one is there hasn't been any studies characterizing noise in distributed settings. This is most likely because there aren't many or any testbeds that are available for DQC exploration. Error correction techniques are, as you might know, an incredibly advanced and complex field that is actively being studied, and many of them have not yet been adapted or have not been studied in a distributed regime, although this is changing. DQC itself is a relatively emerging field that lacks the maturity, perhaps, of standalone quantum computing research, and the progress required to advance in this setting really requires cross-community collaboration between the error correction and the quantum networking communities, or the DQC community, which are two groups that have very distinct toolkits and approaches to their research. I mean, one of the clearest examples of this is when I was writing this paper, I started talking and I developed this idea of global and local ZNE encodings, but in the error correction community, encoding means a very different thing, right? So even then, like at that level of naming things, there's really a lot of miscommunication that happens, and it's very clear from the papers. So I decided to take a slightly different approach, perhaps motivated by my own lack of knowledge at the time, which was exploring error mitigation in a distributed quantum computing setting instead of error correction. So error mitigation is basically a cheaper, more implementable way of combating noise. It doesn't ensure fault tolerance, but it does usually enable noise reductions, and it is very seriously being considered as a hybrid tool with error correction and as something that could prop the future of error correction. Particularly in this work, I focus on a very standard and well-explored error mitigation technique, which is Zero Noise Extrapolation, which I will refer from now on as ZNE. And this is a particular error mitigation strategy where basically the entire idea is that you intentionally scale noise by basically repeating the amount of gates that you're going to do in a way that they're going to commute at the end, so they're going to disappear from the computation. And as you add more and more gates, you are extrapolating the amount of noise that is going to be generated within your device. And your entire objective is to basically create this extrapolation through various levels and take from that what you would assume would be the mitigated value down to where your extrapolation assumes the zero noise level would be. So you're basically backtracking yourself based on the assumptions of how you see your noise scale. Now, as I've said, I studied this mitigation technique within a wider context of a wider question, which is this question of global versus local encodings. So I've been really interested recently in trying to understand how we can include different aspects of quantum optimizations and quantum correction within the pipeline of DQC. So as I've said, the pipeline of DQC is this idea where you start from a very large computation and then you kind of partition it into sub-computations that you assign to different devices within a quantum network. But the question is, if you have things like circuit optimization, error mitigation, error correction, when should you do them? Should you do them before partitioning on your entire circuit, or should you do them after partitioning? If you do them before partitioning, I call this a global encoding because the optimization that you're implementing or the correction that you're implementing is performing the entire computation prior to distribution. I call after partition local encoding because this is when the optimization or the correction is performed on the sub-circuits, on the sub-computations post-distribution. So you kind of have a local view instead of a global view. In this work, I set up this experiment that had 3 algorithms that were tested, and I basically conducted studies based on a custom noise model where the local noise was varying between 0.001 and the communication noise was 0.02. These are values that correspond to the Qiskit noise implementations. And then the communication noise basically corresponded to the local noise multiplied by a value that could be 1, so an equivalent noise, which is not very realistic, 1.1 and 1.2. The tests were repeated over 2 to 6 partitions, and there was this very hard rule that one partition had a minimum of 1 qubit. All the tests were run with the Qiskit Air simulator with depolarizing noise, and the error mitigation was implemented through the Mitig library. Now, I evaluated my results on 3 main metrics. The first one was ZNE error. So this would be the expectation value error that was used to measure circuit fidelity. It's defined basically as the absolute difference between measured and ideal expectation values. The second evaluation metric is error reduction. So this is the fractional improvement in expectation value when ZNE is applied compared to the baseline, aka the non-error mitigated setting. And then depth overhead. So the ratio of the amplified circuit depth after this entire process compared to the original circuit depth. So how much bigger is our implementation? And then I performed the partitioning. So I went from a computation to a graph to a graded partitioning strategy that then enabled distributed quantum circuit. This is probably a very simplified version of what would be considered state of the art, but it's good for our purposes. The graded partitioning strategy was very straightforward. It basically identified clusters of qubits and interactively assigned those clusters or split them up depending on what the target partition balance was. And we assumed that the network was fully interconnected. So we didn't really, again, very simple setting for the partitioning as it wasn't the point of the work. The cross-partition operations were implemented as non-local multi-qubit gates with TP implementation. The results, pointed to quite a few things. So starting with the beginning, it seems that Global ZNE achieves a pretty good improvement over the baseline. There is visible error reduction as partition counts increase, reaching about 48% at 6 QPUs. So as the number of partitions increase, we actually see better and better performance for the global technique. Nonetheless, local ZNE actually shows a much lower and not very clear scaling, and even sometimes, or even, at least more often than in global technique, reaches negative scaling. This means that ZNE is actually worse than running the original circuit, which is theoretically possible given that it doesn't assure fault tolerance, it just usually leads to it. These findings point to the idea or to the fact that Global ZNE is a more effective and scalable strategy within our experimental setup. Beyond this, Global ZNE does impose quite a large circuit depth penalty. So the circuits that Global ZNE leads to are very, very large compared to local ZNE ones, which are in themselves already 3 times the original circuit size. ZNE is expected to make circuits much larger, but there is a real tension here because DQC is realized, or the entire objective arises from this idea that we do not have a device large enough to complete the computation. So if we are now requiring even larger devices, like if we are creating this need for even larger and larger networks of devices, we are kind of, eating our own tail in a sense. So the conclusion here was that Global ZNE performance advantage does come at a significant computational cost. Another finding that came from this was that, as can be expected from the previous results, Global ZNE does perform best at higher partition counts, and with a peak of a reduction of 71% at 6 partitions under moderate communication noise. So the previous results were aggregated over all noise. Here we're cutting it down to every single noise multiplier individually. But counterintuitively, the performance did degrade at lower partition counts despite less communication overhead. So we would assume that the less cuts that we perform, the less noise we would achieve, which wasn't necessarily the truth. So more QPUs can, in a sense, improve, not harm, mitigation effectiveness, which was quite interesting. Then there was also this question of predictability. So how sure are we going to be when we implement one of these encodings that we are going to achieve our desired objective? So Global ZNE did obviously achieve better performance, but it had a much higher median error reduction. It did have a higher median error reduction, as I've just said, but it had a much wider variance in its result. And a lot more outliers, whereas local ZNE actually remained relatively stable and near zero across all levels. So even though global ZNE is a higher reward, as we've said before, it's more costly in terms of the depth, and now we know that it's also less predictable in terms of its behavior. Local ZNE in that sense is slightly safer. It improves our circuits less, although overall it does still present an improvement. It is still heavy in terms of the depth that it requires, but not as heavy as global ZNE. And as we can see now, it is safer in terms of offering more modest gains. There's a few limitations with this study. It is a relatively small study, and it basically only runs over one simulator with a very specific noise model, which is not ideal. We need to study this across more test beds, ideally hardware ones. The algorithm coverage is also relatively reduced, and the network realism isn't great. We assume a fully interconnected setting with zero multi-hop. The mitigation technique scope is also reduced, so we obviously only use one error mitigation technique, ZNE, but even within ZNE there are various variants. So it would be very interesting for other researchers to also explore how other error mitigation techniques, or even other variants of ZNE, other ways of extrapolating back to the zero noise level, could change our conclusions. In general, we are relatively confident in saying that within our setting, global encodings seem to be more effective, but local encodings do continue to be relatively interesting because of that stability that they present. And at the end of the day, they are not making things worse on average. So it might be better for us in the long term to have a more stable solution and work on improving that one than having a very unstable solution, even though it might sometimes offer much better results. The amount of overhead, so this idea that we keep inflating the depth of our circuits, does seem to diminish at scale, meaning the larger our partition counts are, the lower this overhead is. This is very interesting because already in this test, we're assuming a relatively low amount of partitions. We're talking about around 6 QPUs, which obviously in near-term settings would be very high. So I'm thinking that, in the near term, we might be talking about 2 to 4 devices being interconnected in the next 10 years. But later than that, we might be talking about quantum internet setting, in which case we might have more than 6 devices collaborating with each other. So we reach that point, actually. This overhead cost diminishing with the partition sizes is an incredibly good result. Finally, a very interesting part, or a very interesting result that came from this research, was that more partitions, so more noise injections and a higher communication noise, did not consistently degrade Global ZNE performance. It seems that noise in DQC does not affect Global ZNE in a monotonical way, which is not what I was expecting. And yeah, that's pretty much our results. I hope you enjoyed. The paper is available in arXiv and will be published by the Infocom proceedings soon.